Hi everyone, can you hear me? Everyone online? Great, thank you so much for the feedback. So, welcome. We are very, very happy to have a meetup again, and we will have presentation all around ML. And I would like to hand over to Antje from 24 Metrics.
Okay, so hello. I need to share. Okay, so welcome everybody and welcome to my presentation today. I am very excited to be here and hope I can give you a good start into this evening. My name is Antje Geisendörfer and I am a working student at 24 Metrics. And today I'm going to talk about the quality prediction and how we at 24 Metrics use AutoML for our business cases. So let's get right into it. At first, I am going to introduce 24 Metrics to you and give you a little overview of what we are doing. Afterwards, I will explain the concept of the quality prediction to you and explain to you what the business case is. Then I'll come to the machine learning process and explain how we developed and implemented our model. And at the very end of my presentation, I will give you some insights about the outcome and the outlook. So what can you expect next from us? If you have any question about any topic I'm talking about today, feel free to ask them after my presentation. All right, so let's start. 24 Metrics, what are we doing and who are we? We are a growing company based in Berlin with a very international team, and with our products, we focus on cybersecurity in the field of affiliate advertising. The global ad spend greatly increased over the last years, and as you all know, money attracts fraud. It is estimated that 20% of the global ad spend is wasted on fraudsters, and in addition to that, there's an upward trend. So, fraud in digital advertising is an extremely fast-growing problem. And this is where 24 Metrics comes into play. We track clicks and conversions of our clients, so every time a user clicks on an ad or installs an app. And at this point, we offer fraud prevention and fraud detection. So we identify the fraudsters and prevent the fraud before it happens. Why is that so important? Because in the advertising world, there are different pricing models and our clients have to pay every time a user clicks on an ad or installs an app. And with our products, our clients can avoid high advertising costs wasted on fraudsters. Last year, we took this whole concept a step further and we introduced a new service for our clients, the quality prediction. And this is the topic I want to talk about today. With a quality prediction, we can predict a user's willingness to pay. And I'm going to show you in the next slides how this is working. All right, here you can see the process of this whole business case. And I will give you a little example to get a better understanding. So at the very beginning of the process, there is a user. Let's call him John. John is scrolling down his Instagram page and he is seeing some pictures and some reels. And at some point there is an ad for a mobile game where he can build a city, let's say. So he's getting really excited and decides that he wants to play that game. So he clicks on that ad. This click is sent to our products and we check whether this is fraud or not. We approved that click because it was just John and he's obviously not a fraudster, so we redirect him to the App Store. And there he can download the app. This app install is what we call a conversion, and this conversion is also sent to us and a proof that this is a valid conversion. So now John is finally ready to play the game. So he's building some streets and some houses and whatever, and at some point he realizes that he has even more opportunities when he buys something. So he decides to spend some money into this app to get more coins and tools, and at this point we speak of a goal that is achieved and John becomes a high quality user. And these are the kind of users that we want for our clients, because we want our clients to achieve the highest possible profit by attracting many paying customers with a low ad spend. Our clients have high advertising costs because they have to pay every time a user installs the app, even if they are low quality users and won't buy anything. Only 5 to 10% of the conversions really convert into a goal. And yeah, so our clients need to figure out who will be high quality and who will be low quality. But how would they know when they start a new campaign? So let's put it in a more generic way and summarize this process from a business perspective. So what is the problem and what is the solution? Running a campaign always requires regular profit checks to ensure that users will convert into paying customers. That is what marketing experts call a goal. And when a new campaign starts, marketers typically have to wait for 2 weeks to see first results. So the evaluation of the traffic can become very time-consuming and costly. As a solution, we offer a machine learning model that can predict the quality of your traffic based on dozens of factors, for example, from which country is the user or which device is he or she using, so that our clients can get a better indication on the first day of their campaign and can take action, for example, if your campaign is not likely to become profitable. Okay, let's move on to the implementation of our idea. We decided to use machine learning because it enables us to use data from the past to predict future outcomes. We followed the typical steps of the machine learning process, which I guess you all know, but you can also see them here. These are getting the data, preparing the data, choosing a model, training the model, evaluating and fine-tuning the model, and the deployment. And I am going to show you in the next steps a few more details about every step. But before I do that, I just wanted to say that we didn't have to do all these steps on our own because we used automated machine learning. What is automated machine learning? In a nutshell, AutoML does all these critical steps for you automatically with the minimum effort for you. So you just have to provide the pre-processed data and tasks like the architecture selection, the training, the deployment, the model export. All these steps are handled by an algorithm. To make these advantages more clear to you, I listed them here. So you save time and money, it is codeless, it is an easy way to get a high quality model, and it is relevant for both machine learning beginners and experts. And because we use the tool from Google, we could also learn from Google's experiences and best practices. Speaking of that tool, I want to introduce Vertex AI to you. That is a product of Google Cloud Platform and the successor of Cloud AutoML. And this is the AutoML tool we used for our model. So from managing the data sets to the training, to the evaluation, to the deployment, it provides every tool for every machine, all tools for every machine learning step that you need. For us, it was definitely the right way to go because we are already running all our services on Google Cloud, and we had just limited machine learning expertise in our small team when we first start. By the way, to build these internal expertise, we had also great support from the DoiT international team over the whole process. But let's get back to our machine learning process. So what did we actually do? In the first step, we collected and prepared our data. So we queried 6 months and listed 9.5 million conversions. Then we could label the data, so we specified for every conversion whether they converted into a goal or not. After that, we could define new features, for example, the weekday, and then we could analyze it to get some more insights and information and find correlations to define even more features. And once we had our final data set, we could export the data set to a CSV file. We all did that manually using Python and the PyCharm IDE and the NumPy and Pandas library. So let's have a look on that data set. Here you can see a little extract, and every line represents a conversion that has been converted into a goal or not. Here is the target column. The 0 presents that a goal has not been achieved, and the 1 represents that the goal has been achieved. But you can also see some other features, for example, the country, the city, the device of the user, or the status. So did we approve the conversion or not? Because we detected fraud. And in the column next to the status, in the advanced reason, you can see why we rejected a conversion. For example, in this case, we detected VPN or proxy. So once you have your data set ready, you can import that data set to Vertex AI. In this case, you have to select the data type and the objective. In our case, we had tabular data and a classification problem because we want to predict a class, so goal or not goal. And we could upload our CSV file easily from our computer, but you can you have also some other opportunities. For example, you can select the table from BigQuery. After that, you can configure the training in 4 steps, and I will explain them to you now. So at first, you select the objective, which was classification in our case, and for the training method, we chose obviously AutoML, but you can also select a custom training method. After that, you select the target column, but you can also have some other options to configure, for example, the test, train, and validation split. You can select the manual split in this case. In the third step, you have an overview about all your features, and in this step, you are able to exclude some of the training if you don't want to consider them for the training, and set the data type, so whether these are categorical numeric text values or timestamps. And in the last step, you set the budget. In Vertex AI, you pay per every hour that the model is trained, and Google provides a recommendation for that, so how many hours should the model be trained, depending on how much data you have. So now you're finally ready to start the training, and you have to wait for a few hours. And when this is done, Vertex AI provides some interesting statistics and indicators and visuals that can help you to evaluate the model. On the top of my slide, you see the model properties, so the configurations I just showed you. For example, you see that we chose AutoML as the algorithm and tabular classification as the objective. You can also explore the model hyperparameters, so which hyperparameters has been tested by the algorithm and just which hyperparameters has been chosen to be the best, so which are the final hyperparameters. You can also see that we optimized our model for the area under the curve of the precision recall curve. You can see this curve here below is a little bit small, but we decided to do that because we have slightly imbalanced data, and we wanted to maximize the performance and the precision and recall of the less common class, the gold class. And this really worked out because we have a precision and recall of 94%, which tells us that 94% of our predictions has been correct and 94% of our conversions has been classified correctly. You can also see a very good value for the area under the curve of the ROC curve, which you can also see here below. This shows the ratio between the false positive rate and the true positive rate, and we want to maximize this area to have a curve like this that indicates that we have a low false positive rate and a high true positive rate at the same time. Vertex AI also provides some other information, for example, the feature importance. So here you can, this diagram is very close to what we expected before. So the advanced reason, which gives information why we rejected a conversion, the device of the user and the location of the user had the highest impact on the prediction. At this point, I also wanted to remind you that Vertex AI can do the training for you and can provide you all these statistics, but at this point it is on you to interpret these figures correctly and draw your conclusions. So it took us a few trials to get the most effective combination of features because we had so many ideas, and maybe you experienced it by yourself. Machine learning is all about testing, so you test some things and then you train it and then you learn from it and you test something else. So you cannot know the result before you have tested it. And you have the domain knowledge and you know what is best for your business. So this is nothing, this can't be done by the machine. All right, so we tested a lot and now we are very happy with our results. And that brings us to the last step of the machine learning process. And to be very honest with you, I was really involved into this process because it was handled by our engineers. So I can just give you a little overview about the main steps they did. So they exported the model using the function in Vertex AI. Then they implemented it to our product by building a Docker image and deploying it to Kubernetes. And then they tested it. And because the latency, the CPU and memory resources seem very satisfactory, we decided to release that feature to our product. All right, let's have a look on the outcome of this whole process. Our clients are now able to activate the feature in our product fraud shield. And once it is activated, the algorithm calculates a score for every conversion they have. This score tells us how likely it is that the conversion will convert into a goal, and our clients can use this to identify high-quality users. For example, to motivate them to use the app more often and buy something, for example, by making special offers. They can also use this information to identify low-quality users, for example, to place more ads to compensate the costs they cause. Our clients also use this feature in our fraud report, which you can see here. In our fraud report, you can see how many conversions you have per product, per advertiser, and per partner, and how many of them has been rejected, how many of them has been approved. And now with the new feature, you can also see this new column, AI score here, and in this column we aggregated all these individual scores and classified them to get a better understanding. In the first row, for example, you see a very low value, which indicates that there's a low possibility that customers will buy anything. So at this point, our clients should take action and change their marketing strategy. In the second row, you see a high classified value, and this indicates that there's a high possibility that the campaign will become profitable. So our clients should just continue with what they are doing because it seems to be the right way. 70% of our clients actively use the quality prediction, and soon after the launch, we received very positive feedback. For example, our clients have seen a 4.2 times higher accuracy compared to previous traditional methods and 7 times faster results. They also reported that when there is a high value predicted, 2 months after the prediction, they have seen a high go rate, a satisfying go rate. So our clients are happy and we are happy too. And that brings us to the last topic of my presentation today, the outlook. So what can you expect next from us? We are constantly working on our model to consider new trends. For example, you might have seen that we have features like the device, and there are always new devices on the market. And our model needs to know them, needs to consider them. In addition to that, we also want to offer multiple models because we are now focusing on mobile CPI campaigns, and we want to grow in this area. We also want to focus more on clicks. Now we predict whether a conversion will convert into a goal, and in the future, we will also want to predict whether a click will convert into a goal. And last but not least, so we also want to offer customized models for special needs of our clients. All right, that's it from my side. Thank you for your attention, and feel free if you have any questions. I am happy to answer to them.
Just looking in the chat. Yeah. No question up to now. Yeah.
Yes, I have a question about the product itself.
Yeah.
And then another technical question. So you are trying to optimize or to target the right customers based on your prediction.
Yeah.
But normally I think this is already done by the platform which provide you where you doing the ads normally, or am I mistaken? For example, if you are doing on Facebook, Instagram, whatever, they see how the convert has happened, and then try to optimize and to target those customers, right? So.
To be honest, I don't know how it is done now, but I just know that we offer this alternative to the traditional way, and now we predict what will be in the future. So I don't know whether this is done now.
Could it be that the goal is not to install the app, but maybe the goal to make a purchase inside
the goal,
and so you need to optimize based on that, not on the install, for example.
The goal is that the user buys something
inside the app.
Inside the app, right? Yeah.
And another question about deploying the model, like is it automatic, or every time you need to retrain the model, and then you will have, as a result, you will have a model, and then you need to export it somewhere, and there is some manual steps. Like, is it automated, the whole process, or there is manual steps?
We need to deploy it every time we update the model, so there's no automated way. But I don't know whether this is possible in Vertex, I guess, but I'm not an expert for the deployment.
I wanted to ask about the data collection step.
Yeah.
How big was the data set that you ended up with after 6 months?
What was the question? How many data we have?
Yeah, the data set size that you used for training.
We had 9.5 million conversions, but I cannot give you amount of bytes, or I don't know.
I just wanted to, because the data set, I mean, what I would guess is that it would be highly imbalanced, because I would say more people wouldn't buy inside the app than people that would buy.
Yeah, we had a little bit imbalanced data because only 5 to 10% buy something. Yeah.
But it's impressive that you reached those numbers with such a
Yeah. Thank you.
Other questions? Would you like to have a break? Break? Question?
Yeah.
Question?
Of using or like in sort of like the short term or sometime down the track, sort of making use of any other machine learning elements such as neural networks to help you augment all these sort of relations in terms of like conversion ratios. Being able to like more accurately like have an idea of the strength matrix to look for.
Sorry, I really didn't hear you. It was a little yeah, could you repeat it louder?
Yeah, like have you thought like a bit further down the track, like sometime later on, like have you thought of using any other functions such as neural networks to help with any preparation and in terms of being able to like have more accurately sort of like rule out any of the data structure.
I'm not sure if I really get the question. Yeah, I'm sorry.
Also, I can like I can have a think more about it and speak to you later.
Yeah, we can talk about it later. Okay, yeah, that would be great. I'm sorry.
Yeah.
Which kind of data did you actually feed into when you collected the data?
Is it working? Hello?
Hi.
So, which kind of data did you feed into when you collected it? I mean, there are different countries, right? So, different visitors, for example, so not only international people going to one website, but maybe more people from one country in particular. So, how did you actually choose the data when you collected it?
We get all this data from our clients because we use these data to our main business case is to detect fraud, and they send us all these data to be able to detect the fraud. And now we can also use this to do the prediction. And yeah.
So they were basically internationally based and
Yeah, we have clients from all over the world. Yeah.
and only products, no services. So you was
Only
everywhere.
products, yeah.
Okay.
Okay, thank you very much. Are there more questions or should we do a small break? You good?
If you think of some question, you can ask me later.
Yeah, there's also room for more questions later on. Okay? Thank you so
Great.
much, Antje.
Yeah, thank you too.
Everyone. Now, I just wanted to say, or actually introduce myself, because I forgot that beforehand. I'm there. Your stage.
Hi, good evening. It's great to be here at iCampus again. It's actually the second time I am being here, so yeah, thanks a lot for taking your time this evening. Yeah, my name is Sasha, and I work at DoiT as a machine learning engineer. DoiT is an international remote first company, and we have customers all topics around Google Cloud, machine learning, and Kubernetes at zero cost, so you don't have to pay for us. Yeah, if you have any questions, you can either reach out to me on Twitter or you just can talk to me today if you're here.
We're also hiring.
And we are hiring. Yeah. I like it technical, that's why we start with the most important part, something you can take with you after this talk. So no need to make notes. I have slides, 2 deep dive articles, and even a notebook containing all the code, plus some additional code you can take with you then after this talk. And I put this slide again at the end so you have time to make a photo. But yeah, the links are pretty noticeable. I'm going to start this talk with a bold statement. Machine learning teams don't need Kubernetes. Thanks to Google, our daily work with machine learning pipelines got way easier. And how that works, we see during the talk. Yeah, today's talk is all about Google Vertex AI pipelines. It's a serverless product to run Kubeflow or TFX pipelines. And if you're not familiar with those topics, don't worry too much. I cover everything you need to know during the talk. And I also have a deep dive article, so you can take it home with you and have a deeper look into it. Let us start with a quick introduction into ML pipelines and how Kubeflow and TensorFlow Extended are related to Vertex AI pipelines. ML pipelines are there to connect the various steps of your ML solution, and Vertex AI pipeline supports 2 different types of production-grade pipelines, Kubeflow and TensorFlow Extended. But for today's talk, we focus on Kubeflow and running. Kubeflow is built to run on top of Kubernetes, and managing a Kubernetes cluster can be challenging and time-intensive. And that's why Google introduced Vertex AI pipelines, a product to run pipeline serverless. So there is no need for a self-managed Kubernetes cluster anymore. This way, our machine learning teams and myself as a machine learning engineer can actually do what they got hired for, and that's machine learning on not maintaining a Kubernetes cluster. Little disclaimer here, Vertex AI pipelines, of course, also runs on top of Kubernetes, but thanks to Google in a way that ML teams don't need to interact with it. I say that repeatedly, things are simple until you make them complicated, and we also have stickers here, so keep it simple. And exactly because of that, we start with the most simple pipeline possible, just 2 components, without digging too deep into the details yet. If you're already familiar with that, don't worry, we get to best practices and deep dive topics very soon. Because we are implementing a Kubeflow pipeline, we need to import the required Kubeflow pipeline modules. And we go over each of those modules, starting with the first one, the components. A Vertex AI pipeline consists of multiple steps, where each pipeline step is defined by 1 component. The component contains the code that this pipeline step should perform, and it might produce some kind of output as input for the next component. What we see here is called a function-based component, It's the simplest one, it's just a Python function, and with the add component decorator, you can see above the function, we declare that this function is a component, and we do that by using the Kubeflow pipeline SDK. A component could be anything like pre-processing, training, evaluation, or deploying your model to somewhere. So there are no limitations. It could be anything you might need in your pipeline. The pipeline itself contains the components we created, and you can see that the output from the first component, this concat component, is the input actually for the second component. This is how we build our pipeline. We just put them out one after each other, and the output is the input for the next one. As simple as it is, as simple as here. The last step needed is our compiler. The compiler takes our pipeline and creates a pipeline specification as a JSON file. And that's all we need to run our pipeline. We can now go to Vertex AI in Google Cloud, to Vertex AI pipelines, upload the JSON file, or use the API or the SDK and run our pipeline. As you could see, it's just a few lines of code, so very easy. And with that basic knowledge, it's time to do our first demo, just so you get a feel how it will look like if you run the pipeline and how the UI looks, and nothing complicated. And after this demo, we go back to the slides and cover some more of the advanced topics you need if you want to use Vertex AI in production. Let me quickly share my other tab here. What you can see here is the Vertex AI pipelines interface. This is also where Antje has the training for the AutoML product, and this is just another product which is called pipelines. And I mentioned the pipeline is just a JSON, and we now can use this compiled JSON. I did it already before. We can upload the JSON file here, so I take this basic pipeline, and now we click continue. We have parameters. It's now input is stressed, so we concatenate them, and then we revert this string. So now the pipeline starts running, and because I run it already, it's used the data from cache. And you can see this is how the pipeline looks, our two components, and we see those are connected, and in the end, we made out of stressed, we made this there. So this is just a really, really easy pipeline, but yeah, even if you scale it to machine learning problems, it's still the same technology behind. So, back to the slides. So it's no magic, it's indeed very simple, but we all know if we start putting things into production, we realize things might be more complicated, and we find more edge cases, and this is why I have some more detailed topics. The next topics are more loosely coupled, contains everything you might need in a production-grade environment, best practices, some of the more advanced features, and also findings we had with our customers. The pipeline you can see on the right is from our own product, and it's executed around 15 times a day, depending on the customer workloads. I didn't have a single issue since I migrated my workloads from Kubernetes to Vertex AI pipelines, and this allowed me to fully shut down my Kubernetes cluster because I was only using it to run Kubeflow. So it saves me a lot of money, a lot of trouble, because I just write the pipeline and I don't have to do anything with Kubernetes. It's also good for small teams. But the first thing we usually need in a production-like environment, and generally with machine learning, are larger machines, more CPU, more memory, GPUs, of course, depending on your use case. And with Vertex AI pipeline, each component runs in its own job. That means we can define the resources needed on a component level, for example, a high CPU machine for processing, and a GPU only for training. And on the left side, you can see how you can set the CPU, and on the right side, you can see how you can set the GPU. If you don't define a machine type, the default one which is used is a 4V CPU machine and 16 gigabyte of memory. So it's important to understand there is no auto-scaling involved. So if you define a machine type, it will exactly use this amount of resources. So those are available, no auto-scaling involved. This wonderful piece of hardware was until now not officially supported, but There is now a preview running, so if you want to use TPUs for Vertex AI pipelines, you can apply for the preview. But there's the workaround where you can use a GPU from within Vertex AI by using a custom job. And the same workaround also applies if you do distributed training with your data. You also have to apply this workaround. The link is there, so you can see how you can use GPUs with distributed training. Let's get back to the components. At the very beginning of our demo, we saw the function-based components, but there is a different type. Those are container-based components. Those can be really useful if you're not using Python, so any other programming language, or your pipeline is already implemented in a Dockerized way. If you ask me which one to choose, it doesn't really matter. A pipeline in a component as a function, probably added to a Git repository, can be as managed as good as a container-based pipeline. So, and for now we focus on the function-based component because it's the easy entry point. Additionally, Google provides predefined and ready-to-use components. You can simply install them via pip. It's called Google Cloud Pipeline Components. And those components integrate very well with products like Google BigQuery or even AutoML to automate the process of building and deploying the endpoints. And so if you're planning to use any kind of other Google product as part of your pipeline, first have a look if there is already a component for you ready to use. For example, if you want to automatically upload your model to an endpoint to make predictions, there is a component that takes care of that. So you can automate the training process, and in the end of the training, you even can automatically deploy it to an endpoint. So it's fully automated. Let's dig just a bit deeper into components. So we saw already the component decorator. And if we add a parameter, an output component file, we get a YAML file, and this is actually our component. So the output for a component is a YAML file, and those YAML file contains all the information our component has, so metadata like a description, a name, the inputs and outputs and its types, and our actual Python code. Our implementation of our component can easily be shared by using a YAML file you can send to your team. And creating those component specifications is different if you're using a function-based or container-based component. For the function-based component, it's automatically created by the Kubeflow SDK. And for the container-based component, you need to write the component specification on the right on your own. But it's still manageable. And we can use this component to share, we can use this YAML file, the component specification, to share those components with your teams. This makes it very easy if you want to reuse your components in your pipeline, so you can just take it to another team that can take it and implement according to the pipeline parameters. Here you can see you can load it from file or from URL. You can also upload those component specifications to Google's AI Hub, so you can search for it if you have a bunch of components. Parameters are used to pass the data between the components. So in other words, it represents the data that our component either uses as an input or produces as an output. Parameters are used for small types like int, float, string, bool, dict, or lists of them. And with machine learning, we usually also work with larger data and more complex data structures. And for that, we use artifacts. And artifacts are similar to parameters used to pass data between components or even to visualize information. In general, artifacts are used for larger and more complex data like training or our model. And all artifacts are stored in Google Cloud Storage based on a bucket path we define for our pipeline. It is important to understand that most artifacts are nothing else than a simple file reference. So if you are going to implement a CI/CD pipeline or you have to save and load artifacts, just keep in mind it's just a file reference, just a file path, nothing too complicated. But it's a really important part to understand. It's just a file path. Each pipeline one also produces metadata and ML artifacts like the hyperparameters, the data, the code itself, and also the accuracy of our model or any other metrics you might want to log. And those are necessary for the reproducibility of our pipeline, so we need them to understand the changes in the performance of our model, for example. So we can't compare pipeline runs if we don't know what kind of data was used to train our model on. So it's important to track everything that goes in and out of our components and through our pipeline. And this process is called model lineage, where we indeed track everything from the beginning to the very end of our pipeline and everything that goes through. And this helps us answer questions like what data was used to train the model on, which pipeline produced the most accurate model, and what hyperparameters were used to train the model. Pipelines can also be parameterized, so you can pass parameters when running the pipeline, when initializing it. This can be really useful if you need to train on different data sets, or you want to run the pipeline for many customers. You can parameterize the same pipeline. What you can see here is just the UI we just saw, but you can also always use the API or the SDK, so no need to use the UI. By default, our function-based component runs on a Python 3.9 base image, and if you're, for example, using a TensorFlow with a GPU, you need to use a GPU-optimized base image. Same applies for XGBoost, for example, or any other machine learning framework. So you make sure you use always the right base image to fully utilize the hardware resources. We had a customer who was running XGBoost on a TensorFlow-based image, and it was not fully utilizing all the CPU cores, just one instead of all of them. So always make sure you're using the right base image. Python packages that not are part of your base image needs to be installed. So if you need pandas and pandas is not part of the Python base image, you can install it. And here it's important to always pin the versions. So you always stand on this specific version because your pipeline runs on a daily basis, and every time the dependencies are downloaded again, and if you have a breaking change in one of those newer dependencies, your pipeline will suddenly fail. So always pin your versions. This is general best practice, even if you use Python or Node.js, always pin your versions. I mentioned it already that each component is running in its own job, and that makes it very easy for us to monitor the resource consumption on this component level, and we can down or upscale accordingly, so you see a graph and see how many of the resources you are actually utilizing. And if you're already using Kubeflow, you're probably already familiar with many of those concepts, but this is also, which is really interesting, you can define conditions. So the common use case for a decision is deploy the model only if the model accuracy is above a certain threshold, or you even can compare your model to the previous one, and only if it's better you actually deploy it, and otherwise you leave it, and maybe even notify your team and make them noticeable that the model accuracy started to decrease, and they can start investigating. And we also can quickly compare pipeline runs. Metrics and parameters you can define on your own, and you can visualize and compare them. You can see two scores of two pipeline runs, and this makes it easy for us to identify the pipeline where the model started, the pipeline run where the model started to decrease. And because we have all the model artifacts based on the model lineage, we know exactly what data was used, and we can reproduce the behavior and the issue, and know what maybe caused the behavior, the model decrease. Each pipeline run stores those artifacts, and those are all stored in Google Cloud Storage. And you need to make sure if you run a lot of pipeline runs, in order to clean them up, you can set up an object lifecycle, because otherwise they are still there, and it's getting more and more and more, and you have to pay for storage. So you can set up something like edit everything which is older than 13 days. Of course, it depends on your use case. If you're using a Google Client library, you usually don't need to define the project ID as long as the client is running inside of Google Cloud. This is because the project ID is usually automatically determined from the environment variables. In case of Vertex AI pipelines, it's a bit different because it's running in the Google internal, not accessible Kubernetes cluster, and not in your own project. That's why you have to define the project ID, because otherwise it will fail with a forbidden error. So yeah, make sure you set your project ID if you run a Vertex AI pipeline, use some kind of client libraries to access BigQuery, for example. And there are multiple reasons, for example, to interact with a Vertex AI pipeline programmatically. The most obvious one is you want to run your pipeline in an automatic way. You can do that either via the API or the SDK, which is basically nothing else than a wrapper around the API. But there's one important concept which you can see here. They are just pipeline once. So there is nothing like deploying a pipeline or deleting a pipeline. It's deleting you can, but nothing like deploying. So when you want to deploy a pipeline, it's already directly running. So if you implement the ICD, you need to take into account that after you build your pipeline, you push it and it will run immediately. So it's just pipeline once. Keep that in mind. To schedule the pipeline, we can use the soon-deprecated AI platform client. It's basically just a command you can see here, and it creates a bunch of stuff in the background. It creates a cloud scheduler, a cloud function, enables a bunch of APIs, and the cloud function will then call the Vertex API as a proxy. So it's a lot which is happening in the background, and it sounds a bit messy, right? But well, if you actually look at it, it's okay as long as you don't have to update your pipelines regularly. And yeah, if you want to implement the ICD, you need to take into account that there's a fixed storage path if you want to deploy them regularly. Also, how you run your pipelines is affected by this deprecation, so always make sure you're using the Vertex AI SDK and not the Kubeflow pipeline SDK to run your pipelines, because it will at some point be deprecated and not available anymore, and your pipelines would most likely will also start to fail. Like with all serverless products, we only pay if we actually run our pipeline, and Google has a fair pricing of $0.03 per pipeline run, which is cheap, plus the cost, of course, for your resources, like the machine type, the GPU you might use for the time you used it. So it's a very, very simple pricing. There are topics I could not cover today, like the CI/CD process, but I also have an article where I go through the complete implementation process, how you can integrate your pipeline into a CI/CD environment. And yeah, if you try it out, leave me feedback. I'm always looking for better approaches, how you can implement this. And I believe as of today, or at least when I wrote the article, it was the fully documented approach on how you can implement CI/CD for Vertex AI pipelines. And I think it's still the only documented approach. Thanks a lot for your time. Here are the links again. I think we have a couple of more minutes. Yes. So yeah, otherwise I'm also around, so you can ask me anything. And for the audience online, you can also reach out to me on Twitter or LinkedIn, or you can write me an email. Good.
Hello, I got a question. It is related to, for example, I've seen that a lot of your solution, it is like a basic pipeline, machine learning pipeline, right? And you get it deployed in, for example, a specific endpoint of the Google Cloud API, right? And what about those cutting edge solutions? For example, when I want to deploy my model in Jetson Nano or my mobile or something like that, how does it work with Vertex?
Do you want to deploy it to where?
Sorry, what?
To where do you want to deploy the pipeline?
Yeah, but instead of to access to the model using an endpoint, like for example, to get the model and deploy that in, for example, my Jetson Nano or something like that.
Okay, yeah. Mm-hmm. So each component you implement, it's fully free. So if you want to deploy your model to a different endpoint, to another cloud provider, to another device, to your on-premise machine, or you want to upload it to somewhere else, you just implement your own component, which takes care of that. So you are fully flexible. The component could be anything. It could be also a component who sends you a notification in Slack if something goes wrong. So there are no limitations on the component itself. It's just Python or Docker-based containers. So we are really fully flexible. We have seen everything customer doing. They do crazy stuff. They have a full pipeline who also spins up other clusters as well inside of the pipeline itself. So there are no limitations.
Okay, thank you.
Hey, thanks for the overview. Really cool. I have a question about the Kubeflow components, the operators, Kubeflow operators like TensorFlow operator or PyTorch operator, MPI operator. Can they be used easily with Vertex AI pipelines? Because when we tried that with Kubeflow pipelines, it's actually very tricky to combine it, even though both are Kubeflow components.
Yeah, so it's everything you can run into a normal Kubeflow pipeline environment, you can also run in Vertex AI. So it's the same SDK, everything which works in a Kubeflow environment will also work here. Of course, there are some limitations because you don't interact with the Kubernetes cluster, so you always rely on what Google is providing for you, but yeah, they are usually on the latest version of Kubeflow as well, and you just take your pipeline and deploy it, and everything which works in Kubeflow will also work in pipelines.
The thing is, it doesn't run in Kubeflow, so it also doesn't run here. It's the same
then
thing.
wouldn't be one either here. So.
Okay. Still cool.
Between all these differences in pipelines, like between like Kubeflow and have you thought of, or have you sort of planned to sort of iron out any of these like issues with compatibility, like between either of these any of these forms of pipelines? Like, have you thought of devising a container that could sort of interface equally between each of them?
So you mean between TensorFlow Extended and Kubeflow? Yeah, those are basically two different products, right? So you have the TensorFlow Extended pipeline and the Kubeflow pipeline, and those different producers, different teams, and it's a complete different product. TensorFlow Extended is made for TensorFlow pipelines, and it only works for TensorFlow. Kubeflow is agnostic, so you can do whatever you want. You can even implement your machine learning pipeline with C# or with JavaScript if you want. So there are no limitations with Kubeflow, while TensorFlow Extended is just for TensorFlow.
Okay, so everyone, we would take a break again, and there will be hopefully soon pizza again, and another talk. And we will start at, just a second, the talk from Thomas will be at, just a second, 7:40. Okay, thank you.
Da war es immer so. Der hat halt mit dem Trainer und dann hat er mal sich Russland sicher so fallen lassen, dann ist er immer nicht schnell hochgekommen.
So, everyone, dear guests, hello, hello. We would like to continue with our last presentation held by Thomas from Merantrix. How it's, this microphone is straight. How it stays there. And yeah, pizza is still coming. I'm really sorry, I'm waiting, like you. But yeah, happy evening still. And Thomas, your stage.
Yeah, thanks everyone for joining. Thanks for the kind introduction. So I'm Thomas from Merantrix Labs. I'm leading the engineers. So who are we? So we are a crowd of researchers, engineers, and innovators bringing latest AI technology to our clients. And we do this in various areas. First of all, on a strategic level, consulting our clients how they should approach AI. We develop bespoke solutions for them, and we also operate them in the real world. Today, I will focus on the AI development, and we do this end to end. So from ideating the solutions with our clients to prototyping them and also scaling them up for the use cases. So why do you need MLOps here? So we work in various domains with various ML challenges with a lot of clients, all in parallel with many teams. They all have to cope with all the challenges, and in the end, we have to solve critical business problems in the real world. And we do this in production-ready systems, but also we are very heavy on research with our research partners. So we also have to go basically the end-to-end workflow from prototyping to having something which is robust and reliable. And this with all these clients in parallel. And you could say, okay, for all these clients, we have to build something super custom. But as you may know, there are always some parts that repeat again and again. So here, the basic building blocks of basically an ML project. First, you go from data ingestion and loading over the data analysis, preparation, model training, and so on. And in all these stages, you use different technologies. And depending on basically the quality grade that you need, you also need like a bigger technology gun to basically serve the SLAs that you agreed on. Moreover, some parts have to be orchestrated so they can run automatically or in a reproducible fashion. So in the end, you just not have like one cycle of these steps, but you have several of them. And first you may start with some experimentation. So you spin up your Jupyter notebook, try out something, do some EDA. You maybe need some superset or Tableau and try something out. Then you check for the feasibility and you start developing something. Then you want to actually take the solution that you produced and bring it into production. So you also need some operation capabilities here. And after you've done that once and you want to innovate, you have to basically cycle on all these three levels through the workflow that I've shown before. And yeah, what you usually start is what I said, a Jupyter notebook. And there's like a huge gap between just having a Jupyter notebook and actually running it in operation, which prevents a lot of AI projects from succeeding or proceeding to the next stage. So you have your notebook and yeah, you're asking your ops department, yeah, how do I run my notebook in production? They say, yeah, you don't. Start from scratch. Yeah, and then you say, well, I don't know how to run my Jupyter notebook on thousands of machines in my Kubernetes cluster. So I throw it over the fence to ops and now it's their problem. I don't care anymore. Yeah, so what is a better workflow? Actually, you want something like this. This is an example for the Google Cloud. So you have your Git hub where you store your code. Some CI/CD pipeline like a cloud build takes the code, runs some tests, deploys documentation automatically, produces artifacts, stores them and distributes them. You want to have some Kubernetes cluster where you have some debug pod for the Jupyter folks running in the same environment as everything else. When you proceed, you want to take your components, put it into pipelines like Flight, which you can also run automatically. You want some nice experiment tracking and collaboration, run data processing and so forth. And this should all basically be in one environment, so you are reducing these gaps and can easily move from experimentation to a production-grade system. In the end, you want to deploy your model with some endpoints, let them scale automatically and monitor them also for the later ops stage. You don't want that you have to hack all this together, so you're using technologies, for example, like Flux to automatically deploy the latest version of your code into this cluster and let not mess humans around with everything. But yeah, this is a lot of stuff, especially to start a project. And as you've seen before, you don't have to do this once, but you have to do this a dozen of times in different projects, and all of them need some slight different setup. So how do we now scale that? That's a big question, first of all. But another question is, how do we actually also update that in the future? So the problem is, you maybe built the setup once, and then a new technology comes up. So when I started my deep learning career, I started with Theano. Maybe some of you still remember it. I don't think a lot of people use it anymore. And then like TensorFlow was there, like the 0.x version, yeah, was pretty hacky. And then the whole API changed. Then there was PyTorch rising from like Caffe and Torch, and now JAX is popping up. And you have to replace these technologies all the time. Same with MLflow and experiment tracking. There's like the whole ecosystem hasn't settled yet. And what you want is you want to constantly improve your setup. You also don't want to build everything yourself. And you want to actually avoid vendor lock. So they are like end-to-end solutions from some providers. You can buy them. It works for one specific problem, but then, yeah, you are basically fenced in their ecosystem forever, kinda. Or you just start from scratch. And to also cope with various use cases, you also have to stay flexible and need good processes to quickly adapt to these new frameworks. And now we already identified two problems, but there is a third problem, which is the biggest challenge, which is basically the human. So the human has to interact with the computer. Usually if you have like ML projects, experts which are like hard to source, and you have to do a lot of tasks to get this running. So just scaling by experts just caps your volume of tasks that you can do. Moreover, humans usually do things a little bit different every time. So reproducibility is a big problem, and you're already have like huge problems due to like stochastic gradient descent and other parts of your pipeline that you basically have to guard keep a bit to keep sanity. And last but not least, the velocity of basically this whole ecosystem is also limited by human factor, by learning new technologies. This whole ecosystem gets bigger every year. Cycling that with people gets really challenging. So what our basically approach to this is, we are building smart tools to scale machine learning and these complex projects. And how do we do that? I want to share with you a little story from my PhD back then. So I studied in biomedical computer vision and did my PhD there. And how this usually worked in project was, me, the image analysis researcher, built some custom software for a specific biological problem. Then I run this on the data that was produced by the biologist, sent over the readout, then new data was produced. Again, I run my software and so forth, and I spend a lot of my time just getting new data in the right format, sending over the readout. This was like not very efficient, especially because like the main asset was that you were the only one who could write the software, but not running the software. But the biologist also couldn't really understand what the software is actually doing because it was a very special software. So we had a lot of R code there. So if you are familiar with this marvelous technology, you will know what this line of code here does. Something very simple, just gives you an output from 0 to 10. It's very obvious for our experts, for other people. Either they need a lot of time to get into it or they just give up. So what was the solution that we approached? We took our algorithms and we built up these projects, Conda Forge, BioConda, and BioContainers and similar, packaged our software, and then built up a node code solution, which is the Galaxy project, where the biologist could put all these research components together and do their analysis on their own. And this helped a lot scaling these projects to more collaboration partners and enabling computer vision at scale. So now back to labs. How do we approach it at labs? Today I will talk about 3 different software solutions that we built in-house and that help us scaling ML ops to all these different kinds of projects. So first of all, one thing that I want to transport to you is develop an opinionated view on how to solve common tasks. So as I said, there are many common tasks that you have in your ML project. For example, experiment tracking or workflow orchestration. Most of the time, they are very similar what you have to do. Maybe the workflow is not similar, not the same, but how to run the workflow is similar. So be opinionated how you do this best, especially regarding the processes in your organization. So our solution to that is Scaffold. It's a library of best practices containing right now 3 big chunks. One is the integration of different open source libraries so that they work nicely together. Then help us basically to do orchestration because often the UX of these frameworks is not the best. And last but not least, general tooling for monitoring, debugging, and so on that you pile up over the time and can reuse. Second, use infrastructure and best practices as code. So first of all, what is infrastructure as code? Instead of clicking everything together in the UI of the infrastructure or installing everything yourself, you write code that does that for you. It's reproducible. if you want to set up the same cluster again, you run it again and you get the same cluster or change it and you don't have to take care of that yourself. Moreover, you can do the same for best practices. I will get into that later, how we think about that. And this is a result of large combinational complexity of the task that you have to face, because you are not facing like one particular challenge, but you are always facing a slight different challenge in each project. And if you basically do infrastructure as code, you can take the bits that you solved in your last project, combine it in a new way, get a new infrastructure, but keep all the learnings that you've done before. Many tasks can be automated. So put all that stuff into code. This is basically the best practices as code, and everything else you can assist by guiding through a workflow with all the manual steps. And also, what is another challenge is change management, what I said before. So with such a tool, you can roll out new features easily by, again, using the tooling to, for example, modify your infrastructure as code. I will explain how that works for us in the next slides. And you can use it to make your best practices and DevOps in a self-serving fashion. And basically, instead of having like one ops team running everything, you can have an ops team that builds this tool, and the individual teams can serve their infrastructure themselves. And this also helps you scaling. So in labs, we built a dev tool which tries to solve these challenges. So it incorporates project generators. So this is for generating code for new projects and infrastructure, and preserves learnings. And we did this especially to solve this combinational complexity. It also contains more infrastructure as code samples, and also best practices as code, for example, coding standards or standards on how to check for open source compliance. And we try to bake all of these guidelines into a tool, because nobody likes to read long documents. It's just annoying. In addition, our team can contribute new components to this tool via flexible plugin systems. So if you, for example, build a script that helps you with some task, you can add it to the tool and share it with your project team or the whole company. So now I will explain you a little bit, because this was very abstract, how this works in practice. So this is the generator command. So the dev tool itself is a CLI tool, and you can run mxgenerate to execute the generator. So the idea of the generator is basically stolen by software like Ruby or Laravel, where you have something for is an engine for templating, but instead of just templating a whole project at once, you have managed files. So each component that you want to add to your project, you can basically add or remove by a command, instead of templating everything at once. So now let's start a new project by initializing a state. So what is happening? A generator is invoked, which just creates a state file, which keeps track of your project. And then you want to have the basic skeleton for our projects. So you have to enter some metadata to initialize the templating process, and then the skeleton generator is run and files are created. So in our case, some Terraform files are rendered, some infrastructure files like a Docker file, and some Kubernetes deployments are rendered. And then you can apply this Terraform files and all your infrastructure gets spun up. So basically what you've seen before, all these different components are now ready in your Google Cloud environment for your project. So there are many generators for lots of components that we use, and you can combine them freely to get the environment that you want. So now you have a project, you got data from your client, it's unlabeled. You want that your client labels this data, in this case, image data, so you want to host a labeling solution for the client. So there's a generator for it, for CVAT, for example, so you execute the CVAT template in your project. Now the corresponding files for the Terraform deployment, but also domain registration, creation of security certificates, spinning up a proxy load balancer, and everything is generated. And since you have Flux now running in your cluster, gets deployed, you have a project name URL with some subdomain where now your client can access the labeling tool and label the data. If you don't need it anymore, you can reverse this process, and then the labeling tool is gone. And you can do this for various components in your project. So the third component that I wanted to share with you today, I'm very excited to basically share it with you because we want to open source it soon. And it's about the whole process of sharing, loading, and transforming data in your project. So there are a few challenges that you face if you do deep learning at scale, especially at some point you need speed. Because if you have large data sets, every microsecond matters. GPUs are expensive, you run them for a long time, and you are burning money easily. And so you want to make this efficient. Moreover, you want to utilize also everything from the network, the GPU, the hard disk, everything, so that you reduce your costs. Moreover, you have all these different projects. You have NLP data, you have multimodal data, computer vision stuff like images, videos, structured text, graphs, whatever. So you have to be very flexible what kind of data and metadata you are ingesting. And since we are a solution provider, we also get data from various sources and in various formats. So you have to adapt to all these different scenarios. Last but not least, you now have these isolated environments per project, but you also want to foster collaboration. So you train, for example, a model on a very cool data set that you created in a research project, and now want to share this data set also with other teams that want to use that for one of our clients. But this gets cumbersome pretty easily, like what is basically the standard here, how to basically do the accounting for the cost of ingesting the data, and how to actually discover that this data is actually there. So there are lots of challenges how to do collaboration in this very distributed environment. And first of all, we have different APIs that we provide in our solution. One of them is a data stream. And this is basically a chainable iterator in Python. And you can chain different steps together. For example, you can filter data that are going to the stream. You can transform data. You can prefetch it. So in the background, all the data gets already loaded or shuffled and so on. And our goal here was to build something that is very flexible, but also very easy to use. And since you have to solve a lot of different real-world challenges, we also wanted that you can easily integrate the frameworks that you are already using. And also, if it gets too much workload, offloaded to multiprocessing or to a remote cluster like a DAS cluster. So what you, for example, want is, first of all, get your data set from another project, and maybe log that you are ingesting it, also to have traceability that you basically ingested this data set later for model lineage. Then you want to do some transformation of the data. You can do this, for example, as I said, using Dask, or you're using DALI if you want to utilize the GPU. Then maybe some prefetching steps. So everything is already prefetched, so your GPU doesn't stall. And then you forward it to PyTorch and do the actual training. And since you have multiple projects and you want to do this collaboration, you need some way of exchanging this data. And our concept here that we think fits best is thinking of data as a product. So you have your one project team, and this project team offers the data set that they created as a product to others. So they can ingest data from the mesh, basically, from other projects. They can transform it using the technology of their choice, and then serve it to others with standardized contracts. And since data ingestion and serving is based on standardized contracts, everybody else can discover nodes in this mesh, build up a catalog of data sets, and then ingest this data, train on them, create new data sets, and share it again with the rest of the mesh. So how does this look in practice? Because all of this was very abstract. So here's a Python example. So first of all, you discover the catalog from all the nodes that you're currently aware of in your data mesh, which is basically here a catalog from plugins. Then you access ImageNet because somebody is hosting ImageNet for you, and you request an iterator stream from the split, which is here the training data split. And since you want to do distributed training, you incorporate some hooks to distribute the data efficiently between your machines by splitting by the rank of your nodes and also the process, so the worker. So every worker basically gets their own data. Then you shuffle it in a streaming buffer, and this is happening across these shards. So as you've seen before, you have this pipeline of different steps, and after an item pops out of this pipeline, or of one step of the pipeline, it goes into this shuffle buffer, gets shuffled, and then pops out of this shuffle buffer again, and you can use it for the next step, which is transformation. So here you're mapping over the samples, you're transforming your image, not your label, and then go to the next step, which is batching. So instead of doing batching with your framework like PyTorch, you can do it much more efficiently in our framework, and then forward it to your trainer of your choice and fit your model. That's basically it. And yeah, and this is super fast, much faster than the other frameworks around. And yeah, that's it from my side. So if you are interested in one of these technologies or what we are doing, feel free to reach out to me. And yeah, of course, we are hiring. And if you're interested in Squirrel, which was the last component, you can apply for the beta or just sign up for the newsletter. Thank you very much. And yeah, I'm open for questions.
You had a couple of technologies you had there. Why did you use those? I mean, because for all of these, there are 10 different other versions. Do you have a reason why you picked those? Like, especially MLflow, weights and biases, and the labeling you built always yourself, right?
So we are using different technologies depending on the project. So as I said, we have Scaffold, which is our library, which gives an opinionated view on which frameworks to use and how. And this is basically our standard workflow and standard tools that we are using. And if you want, you can deviate in your project from that. So why we have chosen MLflow and want to be. So first of all, MLflow is open and free. You can host it yourself in your own cloud. That's why we have chosen it initially. However, in some cases, for example, Want2Be has more visualization capabilities. So if you need like deep insights into your models, then Want2Be is better than MLflow, like visualization-wise.
What sort of decision-making factors do you think come into play when you're trying to decide on which sort of libraries or which sort of like pipelines to use? Because I'm sure all these would have to sort of factor into your decision-making calculus, so to speak. Like, would that be things like having to justify them to, or like to be able to present them to your client, or to be able to make sure that that's sort of like understood across all your stakeholders and. To what extent does it all factor into your deployment of all these tools?
If I understood you correctly, so there are multiple axes on which we evaluate the basically ML ecosystem. And one of the major axes here is, for example, flexibility. Can we cover all the different use cases that we see from our clients? And also another factor is, can we basically run this component on our own clusters? Because some clients don't want to have everything in the cloud.
Cool.
If it comes to optimize ML workloads, like you presented here, different approaches come to my mind. So, for example, choosing the right or a better framework, using better or more clever pipelines, or just using more powerful hardware as an example. So, can you weigh those three approaches, or are there other approaches that should be considered in situations like that?
I would say most of the time you want to cut basically the work that your engineers have to spend on the implementation. So if you can just throw more compute on it, this is usually cheaper. So this is just a very shallow answer, but in general, in most of the cases, it holds. Thank you.
Okay, so if there are no more questions, we would actually wrap it up for now with the streaming. So thank you so much for everyone who joined. And yeah, I called called a pizza and they said it will take 20 minutes. But they said that 10 minutes before. So crossing fingers. Have a nice evening. Thank you so much. And let's continue. Thank you.